Hello, good morning everybody. Welcome back to Computer Science 4300, C++ game programming. Just a quick funny story before I start the lecture today. I have a lot of technology that goes into creating these lectures and making them live. And sometimes, you know, stuff goes wrong with that technology. And the funny thing is the thing that I had to debug this morning that is something I've never had to debug before and kind of had me in a bit of a panic. You know, I've got 3 different monitors, I've got my audio set up, I've got the video set up, I've had the camera go wrong before, I've had the mic go wrong before. Hello everybody in the chat. But today, I had to debug my desk. So I have a standing desk, and literally like 2 minutes before the lecture goes live, usually is when I put the desk in the standing position. And I don't know if you can tell, but I'm standing up, right? It's much nicer to stand than it is to sit down when you lecture. And my desk wouldn't move. So it gave me this error code, and so I'm like Googling the error code, trying to get my desk to actually stand up. And so I got it to go down, but it was so far down that I couldn't have even given the lecture sitting. I would have been like ducked anyway. I managed to get it done like 30 seconds, like as that countdown was happening is when I finally got it to work. And then when I hit go live, it didn't go live. And so I had, you know, sometimes there's, it doesn't always go the way that you expect. So, all right, what are we doing today? Where are we? We are here. It is October 4th. We are doing sprites, textures, and animations. So that's going to be really cool. So far in our assignments and in our programming, we haven't talked about textures or animations yet. We've sort of been making our own animations by rotating and moving around geometric figures, but nothing when it comes to actually like loading images and displaying frames of animation and stuff. So today we're going to talk about all that, and it's not going to be that difficult. Someone said sometimes they go out of calibration, you need to make it go all the way down. Yeah, so that's exactly what happened to my standing desk. Was there was an error code because at some point someone had tried to move it and it didn't, and I had to hold a button for 30 seconds in order for that to reset. So that was the result of my Googling. All right, so let's get on with the lecture. Alrighty, so lecture number 9. We're going to first talk about some engine architecture upgrades and why those matter. Then we're going to talk about SFML textures and sprites and how we can do basic texture animation in our game engine. So if you recall, you're all working diligently on assignment 2. I'm sure you're not going to leave that till the last minute, right? Okay, hopefully. So here is what the architecture was for assignment 2. We essentially had a game class, and the game class basically did almost everything in terms of the game systems and everything. The game class had an entity manager, which stored entities, and the entities stored components. Okay, so let's have a look at that. We had the entity manager class. That is a factory that constructs and manages all our entities for us. And our entities have a private constructor, so that only the entity manager could handle entities. It has a delayed entity add to avoid iterator invalidation. It also handles the removal of entities. And we have a secondary map from tag to entity that allows us to trade a little bit of storage for a lot of convenience and runtime efficiency. And this can also help us do other bookkeeping, let us know how much memory we're using, how many entities we're creating per second, and all sorts of cool stuff. The game class is this is like a top-level game object. It holds all of our game data, and it holds all the game system functions. It has all the gameplay code, etc., etc. So we have like this stores the window, it stores the entities, it stores the player, stores all these variables that are related to the game, and it has all of our systems as well. So what can this game engine do? We talked about this last time, but it can create game objects as entities. It can add component data to entities. It can implement gameplay via its systems. It can handle system input, or user input, apologies. You can also pause the gameplay and exit the game, and you can initialize and load configurations from file. But what can it not do yet? It can only display one scene, and we'll talk about scenes in a bit. It cannot load texture data or sound assets. That's kind of bad. It cannot display textured animations. We would ideally want to be able to do that. And it doesn't have any menuing. It doesn't have any interface. It just basically has this one scene, right? So again, what is a scene? I think this is probably the third time this course that I've explained what a scene is. So a scene, or a game, can contain many different scenes that have different logic or controls. So for example, in RPG games like Pokemon over here, or Final Fantasy, any of those type of games, we may have different scenes that are completely different. So we may have like a menu or a text or a dialogue scene up here where we're like talking to some NPC, and in that scene, my up and down may be just like selecting options from a menu, for example. Like you can say hello, or you can say go to hell, something like that. Then, once we're done with the dialogue, maybe it transitions us into a different scene where we're walking around on a world map, right? So I'm transitioning from a world map to a town, maybe I'm walking through a forest, something like that. And then when a random battle occurs, now I'm in a combat scene where the game logic and the game controls are very, very, very different. So, how can we modify our architecture to allow for different game scenes? That's what we're going to do now. So in assignment 2, we had just the game class because our game consisted of just, okay, you launch the game, you're in the one scene that the game has. There's no other scenes, right? We're just shooting geometry. That's it. So the game class from assignment 2 handled all the functionality for the game because there was only one type of functionality that we ever needed, was that one attack stuff, right? So it's kind of old school Space Invaders, only one scene that actually does anything. Some of this functionality will remain the same over all game scenes, right? So if we think about our game class, there's some stuff that did that if we had a game that had multiple scenes, we could think about keeping some of the functionality in this one game scene. Right? So for example, no matter how many scenes that we have, we'll still have a main loop structure, right? So that main loop that calls all the different systems, that does the rendering, etc. We'll still have a game window. There's only going to be one of those, no matter how many scenes that we have. We're still going to be loading a config file, no matter how many scenes that we have. And we may want to load all of our assets at once, right? However, some of the functionality will be specific to the type of scene that's currently shown. So for example, the input controls are going to be different based on which scene is there. Maybe the rendering is going to be different based on the scene. The game logic is going to be different. Maybe collisions will be different, all sorts of things. So what we have here is that there's some functionality in our current assignment 2 game class that if we do have multiple scenes is still going to be sort of, the same across all scenes. But there will definitely be stuff that is different between the different scenes. So, let's separate that functionality then. Instead of just having one game class that does everything, we're going to separate the game class into 2 classes which handle all of this functionality. So we're going to have the game engine class, and we're going to have a scene class. Now, just to let you know, there are many, many, many different ways that you can handle this, right? I know there were people watching this lecture series who have done AAA game development who would not do it in this sort of way. This is not the absolute most efficient way to do this. It is not like the definitive, if you don't do it this way, you're wrong or you'll be inefficient. As I've stated multiple times in this course and the architecture that I've chosen is a very fine, delicate balance between efficiency, usability, and learnability for our audience, okay? So just keep in mind, this is an undergraduate course. It's not like 10 years of development experience type of course. And so by separating things really intuitively like this and separating the functionality into different files and different classes, this helps us accomplish our goal very quickly. And later on in the course, I could possibly tell you how you might accomplish this in the most efficient way possible if you were writing like a AAA game engine or something like that. So what do these 2 classes do? Well, the game engine class is going to contain all of the functionality that is the same no matter which scene that you're on, okay? So for example, it's going to handle the window, the game window. It's going to handle running and quitting of the game. It's going to handle the construction and the management of the scenes, for example. That's what the game engine class is going to do. And then the scene class is going to have the functionality that's specific to each scene. And it's only going to hold the entities that are relevant to that scene. Okay, so let's have a look at the game engine class. So over here, I've got a diagram of the game engine class. First, it's going to store all the top level game data. So it's going to store the assets, it's going to store the window, it's going to store the scenes. So over here, right below my, let me move that for a second. So up here, you can see that we have a map from strings to scenes. And what this is going to do is it's going to allow us to store all the different scenes in our game mapped by a string. Now, yes, this is not the most efficient way of doing it. We could have integers or enums or whatever, but this is going to be by far the easiest way to do it with very little overhead. The amount of time that we're actually switching scenes is going to be very, very limited, and so the performance bottleneck of a map from strings to something is going to be very, very minimal, right? We're maybe going to be switching scenes once every few minutes in our game, so it's fine. It's just fine, right? All right. The next thing we're going to store is the window. So this is an SF render window, and so the window will not be changing based on the different scenes. Like the game window is still there, it's still running. The assets. So the game engine is going to store all of the assets, and the way we are going to be doing things in this course is that our games are going to be so small, right, that we are going to load all of our assets at once at the start of the game. So when the game runs, it will load all of our assets for all of the scenes. And the reason we can do that is because we probably have like at most 5 megabytes of assets that we're loading for any game, right? Just a few textures that we're loading for like Mega Man or 8-bit style. If you have a game that's much larger, right, you might want to load your assets every time you switch scenes, right? So if you have a game that's, you know, like some modern AAA game, you might have like loading screens. When you transition from one particular part of the game to another part of the game, those loading scenes are for loading assets because you're not able to store your whole, like, I don't know, Blu-ray disc full of data in memory. So just keep in mind that in our game, it's quite small in terms of asset management, and so we're just going to load all of our assets at once, and so the game engine class is going to store the assets. But if you did want to store the assets on a scene-by-scene basis, you could also do that, but we're not going to be doing that in this game engine. We are also going to be storing a variable which tells us what the current scene is. So for example, if our scene map is currently storing like a menu scene, and it currently has like the gameplay scene, then we're going to store a string which essentially says, okay, this is the current scene that we're playing, and that will help our engine decide which scene to load. And then we have the same thing, like whether or not our game is currently running, and whenever we want to exit, we can just set that to false, and that will clean up everything for us. It's also going to handle all the top level functionality. So for example, the changing of the scenes is going to be done here, as well as the raw handling of the input. So the actual collection of keystrokes and mouse inputs from the user is going to be done at the game engine class. And we're going to be talking a little bit later about how that stuff is handled in the individual scenes. But we're going to be moving away as far as we can so that we're going to trying to be separating functionality from input type. So later on, the game engine will be handling the raw keystrokes and then creating events, and those events will be passed to the scenes. Okay, so the things that have to do the logic about the gameplay don't need to know that things came from a mouse or from a keystroke or a replay file or anything like that. They'll just know, okay, I need to jump now, for example. The game engine run is going to contain the game main loop, and the game engine pointer will be passed to all scenes in its constructor. So this will mean that the scenes will have access to the assets, the window, and the scenes through the pointer to the game engine class. Okay. All right, so now we have the scene classes. Let me move this for a second just so you can see this. Just in the top right, it just says scene abstract base class. So of course you should know what an abstract base class is because you've taken object-oriented programming. And so what does the scene base class do? It stores the common scene data. So every scene is going to have some data in common, right? So it's going to store, for example, the entities in that scene. It's going to store the frame count. So how long has this scene been running? It's going to store maybe the actions that are possible at this scene. The scene-specific functionality is going to be carried out in the derived classes. All right, so this is the base class. We are using object-oriented programming in this course. I know at the beginning that I said, we're not going to be using object-oriented design for our entity component system, but we are using object-oriented programming because it's quite intuitive and it's quite easy to implement specific functionality in that. So the base scene class is abstract. It cannot be instantiated, so that's the way you do this. In C++, you declare a bunch of functions equal to 0. And simulate calls the derived scene update a given number of times. So that's going to be useful later, but essentially we're just changing the way things work a little bit. And this update function is going to handle, that's going to be called by the game engine, and the update function is going to call all of the relevant functions within our game scene. For example, the doing of actions, the rendering, all sorts of stuff like that. So then each scene's derived, I don't know why I can't speak today. Just give me 1 second. So now that we have the base class, we're going to have various derived classes. And so these derived classes, for example, scene play, that might be the gameplay scene. You can see here that we're going to store stuff that's relevant to that scene. So if we're currently playing a given level, then that scene is going to store the level data. It might store the player pointer. It might store the configuration for that scene, for example. The scene-specific systems are defined within the derived class. So all of these systems down here are going to be derived within, or defined within the derived class. For example, the movement. Oh, let me do one more. So some scene-derived classes may require quite different systems based on the functionality. So for example, if you're in a menu scene, you might not care about collisions if you're currently in a menu scene. If you're in the gameplay scene, you might not care about dialogue systems, right? So we're separating that functionality into each derived scene class. However, something that we do need is that the update, render, and do action functions, those are going to be functions that need to be implemented for each derived scene class. So up here in our abstract class, we said that these functions equal 0. So this essentially means that these functions have to be implemented for every derived class in order for them to be instantiated. Okay, so each scene is going to need an update function to tell it what to do on each frame. It's going to need a render function to say how I want to draw this scene. And it's going to need a do action function, which is going to actually allow to the doing of the actions. For example, moving up, down, left, and right. So how are we going to switch scenes then? Well, as you can see up here, let me actually just fix this. Let me move it down a little bit. There we go. So now I'm not overlapping with it. So as you can see over here, the game engine stores a map from strings to shared pointers of scenes. Okay, so we're going to be using shared pointers again for scenes. It also stores a current scene string. So current scene looks up the currently active scene by calling map current scene. That's it. So if we have a string which is this string stores the name of the current scene. So for example, it could be gameplay, it could be menu, it could be dialogue. Whenever we go to say, okay, which scene am I currently running? I just look at that string and look it up in the map. That's it. And change scene is a function, is going to change the stored scene to a new or previously stored scene. Meaning that if I call change scene, I'm just going to change the current scene's string, and then when I go to look up whichever scene I'm in, I just look up in the map that scene. And it's going to just store the pointer to that scene object in the map. It's really, really easy. And this just essentially mimics a finite state machine for scene switching. It's like the easiest possible way that you could implement this. I mean, okay, you could have a vector and then like iterate through the vector, and that might be conceptually easier than what a map does, but this is like the easiest way of actually implementing it, in my opinion. So here's an example. Here's a scene switching example. When the game engine is first constructed, you're going to need to enter some sort of scene, right? So when the game starts, you have to say very specifically, here's the scene that I'm on. So what we're going to do is when the game engine constructor runs, we're going to say change scene menu. So this menu is going to be the name of the scene. And then SP here just means shared pointer. And then this will be a shared pointer to a scene menu. So this is the menu scene constructor. So inside change scene, I set the string of the current scene equal to menu, because this is the current scene that I should be showing. And then in the map scenes, I say scenes menu equals make shared this, right? Or this scene that I've passed in. So that's it. You just set the current scene and then you set the value within the map. That's all you have to do. Then the player is presented with the menu scene. And now, while the player is moving up and down, let's say that the player selects to start the game. So if the player selects a level or to start the game, then I'm going to have a level path, right? So this is a level path. That's maybe the first level of the game. So that might be level 01.text. The menu is going to tell the game engine, hey, someone clicked start the game, so I'm going to change scenes. So whenever I change scenes, all I'm going to do is the game is going to say, hey, the scene is going to tell the game engine to change scene to play, and then give it the constructor of the scene play with the level path. That's it. It's just one call to change scene, and change scene has a map. A game engine has a map, which is referenced by a string. So if I say change scene, and then I give it a string, it's going to change scene to that stored scene. That's it. It's really, really that simple. Okay, so now that we've talked about how to change scenes, let's talk about how we're going to manage assets. Asset management is very important. What is an asset? An asset is an external file that's loaded into memory to be used in a game. So for example, in our game, assets are going to be textures. So these could be image files. We're going to be working with PNGs for transparency. You could also have JPEGs, bitmaps, all sorts of texture files. They're going to be animations. So our animations are going to be textures plus some bookkeeping. We'll get into that in the last half of this lecture. We're going to have sounds. So sound files, SFML natively handles .wav files and .ogg files. WAV files are sort of raw sound files uncompressed. OGG is an open source, lossless, compressed format that SFML supports. As far as I know, it does not support MP3 files because of MPEG licensing issues. It can also support fonts, so we are going to be loading TrueType fonts into our game assets. And the number one rule of asset management is load once, use often. So, for example, we would not want to be loading image files every time we want to display an entity, right? So, for example, if I had an entity of Dave in the game with an image of my face, I don't know why you would put that in a game, but what we would not want to do is every frame of the game create a new object that has to be rendered and then load the data from the file and then draw it to the screen, okay? Loading files from disk is the slowest part of any game engine. So what you want to do is at the beginning, if possible, if all your assets are small enough, load everything into memory and then load it once. And then whenever you want to draw Dave's face to the screen, I hope you don't, but if you do, one group actually did for their final project. That was kind of a silly project. But you'll only load Dave's face once, right? And once it's in memory, you can just refer to where it lives in memory. You don't need to keep loading it, okay? So load once, use often. I think even the industry people will agree with me on that one. So we're going to have an assets class that stores everything for us, okay? So we want to load assets, and we want those assets to be defined in an external configuration file. Now, when it comes time for assignment 3, I'm going to get into the real details of the configuration file, but you can have it, you can think about it in your mind as something like this, where we have a bunch of different lines in the file, and the lines are going to tell us what to load. So for example, we might have one line that says, I want to load this texture. I want to give that texture this name, Mega Man, and I want, and the location of that texture is here on disk, okay? So this texture is called Mega Man, and you load this PNG file for that texture. Similarly, maybe I want to store a sound, and so I'm going to say load this sound. It's called Megadeth, not the band, but like maybe when Mega Man dies, there's a sound, and that sound asset is stored here. Okay? And then later in our game engine, when we want to get access to these things, we are going to reference the asset via the name that we gave it in the configuration file. So I can say, hey, assets, get texture Mega Man. Hey, assets, get sound Megadeth. Right? So, now, again, this is a trade-off between absolute efficiency and usability. Right? If you were making a AAA game, again, and you wanted to be as fast as possible, I'm sure that instead of giving these string names, you would give them integers or enums or whatever, but the amount of times that we are actually calling get texture and stuff is so low that this is fine. This is very efficient. We can display thousands, if not tens of thousands of things per second using this. So, to implement this, the asset class is going to have another map, and we're going to be mapping from strings to asset types. But just keep in mind, again, this class is a balance between usability, learnability, and efficiency. So no, this is not the absolute fastest way to do this, but it is the easiest way to do this, and it is still quite efficient. So if you were to do this and you wanted absolute mind-blowing efficiency, then instead of a map here, you may just have a vector, and that vector is indexed by some integer, and then you would have a big long list of enums of all the different assets that you would have somewhere, but we don't want to do that in that course. It's a lot of work, it's a lot of managing of the enums and stuff, so, but just realize that this is not the fastest way of doing it. So you don't need to write books in the comments about me using maps of strings to stuff. I know that it's not the fastest way to do it, okay? Because I do get the most annoying thing about teaching this course is the actually, you know that meme, actually people in the comments who are just like, I've had 20 years of experience on games and this isn't the fastest way. I know that it's not the fastest way, but it's fine. It's fine. Trust me. For the context of this course, it's fine. So, the assets class is going to look something like this. It lives inside the game engine class, because the assets are going to be loaded once. The assets for all of our scenes are going to be loaded once when the game starts up, okay? And it's initialized inside the game engine's init function. So when the game engine is constructed, we call the init function, and that's going to load all of this. It's going to be accessed via the scene's pointer to the game engine. So each scene is going to have a pointer to the game engine, and then through that pointer, you can get the assets, right? So the assets class is loaded once at the beginning of the program. It can then be used in any scene, but it's only initialized once in memory, okay? So for larger games, as I said, you may want to do like scene by scene asset loading. That's fine. But for example, loading screens on level change in most games are for asset management and other data loading purposes. So what we're going to have inside this class is we're going to have a map for each of our data types. So we're going to map from strings to textures, from strings to animations, from strings to sounds, and from strings to fonts. Okay, so anytime we want to get access to any of these things, we just refer to them by their name. It's going to be really, really easy. And if we want to add a texture to our assets class, we'll just call add texture with a name and a path. And similarly with sounds, animations are a little bit different. I'm about to get into animations though. And then whenever I want to get a texture, it's just say get texture name, get animation name, get sound name. So it's the easiest possible way that we could construct something like this, is just associate every type of asset with a string and then use the string for the setting and the getting. And again, it's not the absolute fastest way to do it, but the amount of times that this is actually done, this is called at most once per entity creation. Okay, so no, we are not calling this map on every frame of the game. It's called once per entity creation, which isn't that bad for a map lookup. But again, we may want to do this with integers if we want to do the fastest possible thing. So I've been talking about textures and animations, but now I'm actually going to describe what they are, right? I'm sure that you all know what a texture is and you all know what an animation is, but in the context of this course, exactly what is it? So here we've got some example, textures and animations add a lot to your game. That Geometry Wars game is pretty cool, but you can only go so far in game programming making games that have no textures in them. So what is a texture? A texture is a graphic mapped to a shape. So a texture, for example, can be generated dynamically or loaded from an existing image file. And we're using bitmap files. And so no, bitmap doesn't necessarily specify the BMP extension. There are different types of image files that you could have. Not all of them are raster images. Not all of them are bitmapped images. But a bitmapped images is essentially just, your JPEG file, your PNG file, just a square object storing image data, RGB values per pixel. So a rectangular shape with a texture attached to it is typically called a sprite. And sprites are very, very common in games. And so we are going to be using sprites, SFML sprites, which are essentially, as I said, just a texture and a shape. And so we're going to take a texture, which is from an image. In our case, we're not dynamically generating textures in this course. If you want to dynamically generate textures, take my other course, 4303. And so if we have a texture and a shape, that's called a sprite. And sprites used to actually be implemented in hardware. So at the very end of this lecture, I'm going to have a link to 2 YouTube videos. I really want you to go watch those videos because they talk about how graphics used to work in older computers. And after you have watched those videos, you will be very, very happy to be using SFML, let's just say, because what you used to have to do to get sprites was insane. But anyway, so if we have, and this is all on the graphics and sprites tutorial for SFML, if we have some rectangular thing, for example, a rectangular entity in our game engine, and a texture, and we map that texture somehow to the entity, we get a sprite. And then we can just call window.drawSprite. It couldn't be easier. If you've ever worked with OpenGL and you've tried to load PNG files and you've had to install zlib and get that to work and then convert your RGBA to RGB space and set your bits per pixel and all that kind of stuff, it's a nightmare. There's a reason we're not using OpenGL in this course, and it's because we would spend the first 24 of 25 lectures explaining how to load an image in OpenGL. I'm sorry, OpenGL, but you're difficult to use sometimes. It takes a long time to learn OpenGL, let's just say. So SFML does all of that stuff for us, and it's so nice. SFML knows many common image formats, and it can load textures from files. It's excellent. It's good enough for this course, okay? So how do we do that? Well, we can call SF texture. So SFML texture, we give that a variable name, so that's texture. Then texture has a function called load from file. And we can call load from file on an image file. And then this, if the loading of that texture was successful, it's going to return true. If it's not successful, then this not texture.load from file will call, and we can throw out some error. So this is like very basic image loading error handling in SFML. But that's it. You create a texture, you load from file, and then that data is loaded from file for you. If you want to create an empty texture, you can do that as well. We're not going to be doing that in this course necessarily. I mean, you could. Don't get me wrong, but for like assignment 3, you won't need to do anything like this. But you can create a blank texture that then you can modify somehow. Here's some ways that you could update the content of a texture. So if you really want to, you could use a raw array of pixels, and then you could set the RGB value of those pixels manually. And then you can use those pixels to update the contents of a texture. So you can get as low level as you want to with this. So if we wanted to, we could say, write some noise generator or something like that to generate the textures in our game. So we could set the raw pixels and then update the texture. We could load an image file and then update that way. We won't be using that method though. Or we could actually update a texture based on the contents of a window. And so one of the cool things that you can do in SFML really easily is create a texture from the contents of a window, and then you can write the contents of a texture to a file. And that would be a screenshot. So you can do screenshots really easily with SFML as well. However, sometimes the texture will not be the same size as the entity's shape, right? So if we have in our game, for example, if we have an image file that's this big, and we have a entity that's this big, how do we map the pixels from this to this? Okay, I'm pretty sure by default what happens is that it will just squish downwards and upwards. It'll just it'll squish to fit. Right? And so I'm sure you've all seen that in a game before where the texture like aspect ratio is a little bit off. So if you had this square like Instagram beautiful image of Dave's face and you wanted to put it on this like really squished rectangular object, it would just squish my face down to fit that by default. However, if we want to say pick a sub-region of this image to actually use for this rectangle, we can specify that when we load the texture. We can also specify it in the sprite later if we want to. So we can load a texture from a file, and we can say only load this part of that image. And that is what our texture is going to be, okay? So a texture is not only the loading of an image file, but it is also the part of the image that we want to draw to our sprite. Okay, and you can specify that. By default, it's the whole thing that will be squished, but we can manually specify it with this command right here, which is an integer rectangle, which has, it takes in X and Y, so that's the XY location within the rectangle, and then the width and height of the texture that we want to load from that rectangle. So, oh geez, don't tell me that I had that whole thing done here. Okay, I'm going to say it again. So sometimes the texture will not be the same size as the entity's shape. Do we want to resize the entity? Well, that might affect gameplay. Resizing the texture may be expensive, so we can specify a sub-rectangle of the texture which is going to be drawn. The entire texture is still loaded, but not all of it is drawn. And so I just explained this. So for example, if we only want to take this part of this texture, then we may specify like, okay, it's 5 in the X direction, 30 in the Y direction, it's 64 wide and 32 high or something like that, whatever this happens to be. And so a rectangular entity right here, plus a texture, and the specification of what part of that texture goes into the entity, that's what our sprite is. And this is going to be how we actually load our animations, which is really cool. So we're going to have one big image that stores all our animations, and then we're going to be specifying sub-rectangles of this image to be what we actually draw for our animation. So let's get into that. Well, we'll get into that a little bit later. Creating a sprite. So how do we create a sprite now that we have a texture? Well, it's very, very easy. You just say SF Sprite and you give it a variable name. Then you say sprite.setTexture with a texture. And then at some point in your rendering system, you just say window.drawSprite. That is it. So how you specify a subrectangle of a texture to draw for a sprite is very easy. So let's say that you specified, you loaded, trying to switch to the pen here in PowerPoint. All right, say you specified this image, right? Actually, let's say I specified this one. So I loaded this big texture for my sprite. Instead of loading a different texture for every frame of animation, I instead say I want to load this rectangle of that texture to be displayed for this frame of animation. And so this is how you actually specify that. You say sprite.setTextureRect. So set the rectangle within the texture that I want to display. And I'll give it some parameters over here, which is the X, the Y, the width, and the height. That's it. That's how we specify that. How is the sprite actually implemented within SFML? Well, it is a very, very lightweight object. So it consists of vertices, a texture pointer, and a rectangle of the texture to draw. So what does that mean? Well, down here, this is literally copied and pasted from the source code of the sprite object within the SFML code. So you see here that a sprite consists of 4 vertices. So the vertices are the XY location of the 4 points that actually are going to be specifying the geometry within your game world. And that's set for you by the size of the object. You won't have to worry about manually setting those vertices. It has a pointer to the texture for this object. That's very important. And we'll talk about that in a bit. And it also stores the rectangle, which is the defining area of that texture that you want to draw to the screen. So even if you load a really big texture for your sprite, all the sprite stores is a pointer to that texture. So that texture is going to live somewhere in memory, right? It's going to be loaded once, and then the sprite just stores a pointer to it. So every sprite does not contain a separate copy of that texture. So that's why we can display however many sprites that we want, thousands and thousands of sprites, because they're not all, like for example, if this texture was 1 megabyte and we have 1,000 entities using that texture, well, that texture is only ever taking 1 megabyte of memory, right? And then each sprite just has a pointer to that texture. So we have 1,000 pointers, but we don't have 1,000 textures, okay? Very important. So sprites store pointers to textures. So here's something that I did that is kind of bad, but your textures, well, it wasn't bad, it was kind of naive because I didn't realize that sprites were storing textures. So let's just have a look at this code. So we're going to have a function which maybe returns a sprite for us. This is not going to be how we do it in our actual game, but this is just, it demonstrates to you something that could happen, which is very unsafe. So the sprite, we're going to have a function called load sprite from a file name, right? So what we're going to do is we're going to create a texture object in the local scope here on the stack. Then the texture is going to load from file, that file. So we've got our texture object that has now been created here. And then we're going to return an SF sprite based on that texture. However, the texture object is destroyed when this function leaves scope. So now we've got a sprite storing a pointer to a texture object that no longer exists. And so this would probably either crash when we tried to run it, because it's trying to dereference some pointer that no longer is allocated in memory, or it would draw like a white box to the screen or something like that. So this can take a couple of minutes to maybe understand, but this texture implements RAII, remember? So when this texture object in its constructor, it creates the memory for the texture, it calls the heap, it says give me memory for this texture, and then when this function, when the scope of this block exits, this texture's destructor is called. And when a texture goes out of scope, it's going to free the memory for that texture. But the sprite was only storing a pointer to the texture. So this means that our textures, if we just load them once, have to have a duration, like the lifespan of that texture has to be the duration of my game, right? So that's where the assets class becomes very useful. The assets class is going to live as long as our game engine lives. And so whenever we get access to these textures, we're going to be sure that they exist for the duration of our program, right? So the lifetime of assets that we point to is very important. Okay. Colors. We can color our sprites as well. So, for example, if I load this sprite initially, right? So I have, this is exactly what the image file looks. If I set the color of that sprite equal to green, then it will add a green tint to that sprite. If I set it to gray, it will add a darker tint to that sprite. So for example, if I loaded Mega Man and then set the color of Mega Man to purple, now I have like Quick Man or something like that, right? If I set the color to green, now I have Woodman. And so it's really cool. You may not need to have, like if you want to have 5 different colors of Mega Man, you may not need to have 5 different sprites. Or sorry, 5 different textures. You could just get away with coloring the one texture via the set color object. And you can also set the transparency of things, etc., etc. Texture smoothing is also very important, because if we shrink or grow an object within the window to be displayed bigger or smaller than the actual texture itself, we may want to set the smoothing property of that texture. So whenever we load a texture, typically for modern games, you want smooth textures, okay? So you would say set smooth to true whenever you load that texture. And then when you scale that object, you're not going to get these really jagged, it's going to do anti-aliasing for you, all sorts of stuff like that. So you won't get these jagged corners of your textures. We could also have repeated textures. So for example, let's say I had a texture that was this, I have a texture that's this big, but I have an image file that's this big. So what you can do is if you give a texture a specific size and then load in an image of a different size, by default, it will just stretch it. So the default behavior is to stretch to fit the texture. However, if you set repeated equal to true, it will sort of tile it on the texture rather than stretching it. So there's this option as well. We won't be using that this in this course, but it's just there if you ever need it. You can have different transformations on sprites. So for example, set position. So just like you set position of the shape in assignment 2, you're going to be setting the position of the sprite to be drawn in assignment 3. You can move a sprite, you can rotate it, you can set its scale, etc., etc. Here's something that we're going to be using for assignment 3, and I will say this again when we get there. If I want Mega Man to be, let's say I want Mega Man to face to the right when I'm running to the right, or face to the left when I'm running to the left. You may think that I'm going to have one animation of running to the right and another animation of running to the left. Well, it turns out in SFML, I can set the scale equal to -1 in the X direction, and it will just flip along the horizontal, and it'll be really convenient. So I'll get back to that, but the scale is going to allow us to shrink or grow an object, or even flip it horizontally or vertically, which is great. Texture sheets. Traditionally, games can have many, many textures, right? We're going to have like a bunch for Mega Man, a bunch for different tiles, etc. It can be hard to manage all those files sometimes. And so texture sheets can be used to store many textures within the same actual image. And it's kind of an easy way to organize and store images. And if the entire texture sheet is loaded into graphics memory, less texture swapping actually occurs. So that's actually really good for your graphics card, and especially in old hardware. So if you look up the textures for, say, Link to the Past, this is SNES, this is one of the texture sheets for Link to the Past, you can see here that it's one sheet, but all the different animations are different rectangles specified in this sheet. So in somewhere in the rendering logic for Link to the Past, they have specified the rectangles for all of the different animations, and this is how they actually get played inside the SNES. You could have, you could load a texture sheet like this, so you can have a town or village that has lots of different textures all loaded in one file. So instead of loading a different texture for every character, every pose, every tile, you just figure out which sub-rectangle is going to be drawn. That's it. So rectangles can be stored as variables or can be computed dynamically if we have to construct the sprite. If we construct the sprite sheet very cleverly. So I'll explain what that means in a minute. But for example, you might be able to say, okay, well, back here, the first frame of the texture of walking for Link is at this rectangle. So we would have to specify, okay, the walking texture is specified at this rectangle within the sprite sheet, okay? Or we could have some other cleverer system for locating things. Texture-based animations. So now we can see here how we are going to be creating animations in our engine. So animation is a sequence of images that when played quickly appears as motion, right? So everything you see on the screen, you see me moving right now, this is just a very quick sequence of images. Any movie you've ever seen, right? You all know how animation is done. So animation is just a quick sequence of images, and when you play it quickly, it looks like our brain thinks that it's moving when it's actually not moving. There are many, many different ways to do animations in games, and sequences of textures is one of them, okay? So texture animation can be achieved by quickly displaying different textures. We saw that in assignment 2, we did a different type of animation where we just set the rotation of something, right? There were no textures in assignment 2, but things looked like they were animated. So bitmap animation, or raster animation that it's called, is animation that's made from pixels rather than in some other thing may have like vector animation, for example. We won't be doing that in this course, but we are doing bitmap, or what's called raster animation, which is just a series of textures that we're drawing in a row. So how are we going to implement this efficiently within our system? Well, we are going to have animations that are all defined within one image file. So just to let you know, I am not going to be giving you a huge texture, like a tile of textures. What did I call that? A texture sheet. So for this course, I am not giving you one huge texture sheet because that gets quite, that encroaches on the usability side of things. And so yes, that would be the most efficient way to give you all of your textures, all of your animations, would be a single sheet for everything. But I'm basically just going to be giving you one texture per animation. Okay, and then you can specify which animation just by a string. So for example, this is going to be the mega run animation. So it's a trade-off between usability and efficiency. But this actually turns out to be really efficient as well, especially with modern graphics cards. So how are we going to implement animations? Well, we are going to have a texture that stores each frame of animation. That texture is going to have some sort of width, right? So this is the width of the texture. It's also going to have a height. And we're going to specify how many frames of animation that this texture has. So what we essentially have left to do is to figure out which frame of animation we want to play and how to specify the subrectangle of that texture to grab the specific pixels that we want to display. So how will we do that? Well, The frame width, so for example, frame 1, how do I get the width of that? Well, it's really, really easy. I just take the entire texture width and divide it by the number of frames of animation. Our actual animation in our game is actually going to have 4 frames of animation, but this fit on the slide a bit nicer. So I'm going to have to figure out which rectangle to draw. Oh, and by the way, I'm also giving you like just a line rather than a 2D sprite sheet where you have like, you may have a grid. All your animations are going to be specified in a row in a line. So frame 1, 2, 3, 4, 5, 6 from left to right. So just to make things a little bit easier for you. So the rectangle I'm going to want to draw is specified by the XY of the top left and a width and a height. And the formula for that is really easy. It's the current frame of animation times the frame width, and then that's the X coordinate. So for example, for the first frame, this is going to be the top left, this is going to be the width, and this is going to be the height. So the first frame is frame 0. So 0 times frame is 0. It's going to be 0 in the Y, right? Because our texture sheet is always going to have the same height as our animation. And then we give it the frame width, which is the total texture width divided by 3. And then the frame height, which is just the height of the texture. So that's how we specify the rectangle. So if this is our formula for the first frame of animation, here's the subrectangle of that texture that we want to draw. It starts at 0, 0. It has width, and height, frame height. The second frame of animation, the X coordinate is now going to be at the frame width. So 1 times frame width, 0 in the Y, frame width, frame height. Frame 2 is going to be 2 times frame width for the X, 0, frame width, frame height, etc., etc. So however many frames of animation you have, you take the current frame, like frame 1, frame 2, frame 3, then you multiply it by the frame width, and then all of this stuff stays the same. So it couldn't be easier than that, specifying an animation. How are we going to actually implement this? Well, we're going to have an animation class. And this animation class is just going to handle that bookkeeping for us. And I've gotten comments in the past that this sort of, it goes a little bit against our sort of pure ECS. So the way we are going to implement this is we're going to have all of our variables related to animation inside an animation class, and then an update function that provides the logic to progress the animation. So we're going to have an animation component, and the animation component is going to store an animation object. So this is a very slight departure from our pure data in components, because the animation class that we store in the component is going to do a little bit of that for us. But it just keeps a lot of that, like, animations are a very set thing that only do one specific thing, right? They don't interfere with any of our other systems, and it's just going to make things so much easier if we just store that in the animation class instead of making an animation system. And animation, the logic that drives animation is going to be the same across every class, or every scene as well. So we would not want to have to implement in every different derived scene all of the logic of how to progress animations. Okay, so that's why we have this logic in the animation class. So inside our animation implementation, sorry, just give me 1 second here. We are going to have some variables. So we are going to have the following variables. We're going to have a frame count. That's the number of frames of animation that this animation has. We are also going to have a game frame count. So game frame is essentially going to be the number of game frames that this animation has been alive, right? So for example, if our game is running at 60 frames per second, and this animation has been alive, running, for 180, or so for 3 seconds, then this game frame would be 3 seconds times 60 frames per second, meaning 180 frames. Okay? So I understand that the word frame here is a little bit overloaded. For example, we have frames of animation, and we also have game frame count. right? Frames per second. So these two things it makes it a little bit more confusing. But frame count, that's the number of frames of animation in the animation. Like there's 3 different images that we want to display. Game frame, that's how long this animation has been around in terms of actual game frames. So the size of this texture is simply going to be, or the size of a frame of animation, right? This is the size of the animation. That is going to be the texture width divided by the frame count, right? This is exactly what we did back here. Texture width divided by frame count. Then the texture height is going to be the height of the animation. We are going to have a variable called animation speed. Animation speed, if animation speed, for example, is set to 10, it means that we want the animation to transition from one frame of animation to the next every 10 game frames. So if animation speed is set to 10, then the animation is going to be transitioning through frames 6 times per second. 60 frames per second, animation speed 10, 60 divided by 10. Okay? This should actually be like animation duration or something like that, but I just called it speed. So on each update of the animation, so our animation class stores all these variables, and it's going to be, update is going to be called on every frame of the game. And so what's going to happen? Well, we're going to update the amount of frames that this animation has been alive. That's the first thing that we do. Then we have another variable, which is this animation frame. That is going to compute and store the current frame of animation that we want to display. That is going to be equal to the game frame divided by speed mod frame count. So what does that mean? Well, let's go back. So we're trying to figure out the current frame of animation that we should play. So let's say that I'm trying to have like numbers here that make sense. So let's say we are at frame 100 in our game. Okay. And we have 3 frames of animation and our animation speed is 10. So if this animation has been alive for 100 frames and our speed is 10, so I take 100. Okay, let me take the animation speed to be 20 just so I have different numbers. Okay, so my animation speed is going to be 20. So I take 100 game frames, divide it by 20, and so I get 5. Okay, now that 5 means I want to be playing the 5th frame of animation of this animation, right? But I only have 3 frames of animation. So this means that, I'm going to start here and I'm going to loop back to the start, loop back to the start, loop back to the start. Looping back to the start essentially is just integer remainder, which is the modulus operator. So if I take 5 mod however many frames of animation that I have, 5 mod 3, right? I'll get 2. And so this is the frame of animation that I'm going to be playing. So that's what this is doing. So just think about that for a little while. So I'm taking the current frame of the game, that was our 100, speed, that was our 20, and the frame count, that was 3. Okay, so that's the animation frame that I want to actually play. So how I figure out the rectangle to be drawn is I take that animation frame, multiply it by the frame width, and then I have 0 width and height for the size, and then I say sprite dot set textured rectangle. And what that does is it tells the sprite to choose this part of the texture to draw. It tells the sprite to choose this part of the texture to draw, or this part of the texture to draw, and then it'll draw that to the screen for me. So the texture never moves, right? The texture is loaded into graphics memory once, and then we tell the graphics card, well, we're not telling the graphics card directly, but SFML is doing that. We're saying, hey, SFML, I want to draw only this part of that texture. And so it never loads the texture more than once. It never moves the texture around or copies the texture or anything like that. It just says, draw this subframe of the texture. So it's a very, very efficient way of playing the animation from a single texture. Now, we will make an animation class for that, and when I go into the details of assignment 3 and I show you the code, I'll go over that animation class with you. And so, the animation specification details, the animation details are going to be specified in the assets file. And how we construct an animation is going to be kind of in two parts. So each animation is going to need two things. It's going to need a texture and a number of frames and a speed. So I guess three things. So at some point in our assets file, we're going to load a texture. That texture is going to have all of the frames of animation in it. So for example, this is exactly what assignment 3 is going to look like in the config file. It's going to specify texture. Here's the name of the texture, and here's where that texture is stored. Okay? Then at some point following that, in the configuration file, we want to specify the animation. So this animation is going to be given the name run. Here is the texture that this animation is going to use. It's going to have 4 frames of animation, and the speed is 10. So the animation class stores this data. It's going to store the name of the animation, a pointer to the texture that it wants to load, as well as the number of frames of animation and the speed of that animation. And then the texture is not actually stored in the animation. It's stored in its own thing. And then this animation just has a pointer. Well, it has a sprite. So the sprite has a pointer to that texture. So no matter how many animations we have that use, like for example, we could have 1,000 Mega Mans on the screen, all playing different frames of this Mega Man running animation, and only one copy of that texture would ever be in memory. And we're just specifying what subrectangle of that texture to draw. So here is the final architecture for assignment 3. Look at this. So the thing that I'm covering up here is the entity. Oops. Why is my laser pointer not working? All right. So up here you have entity class. That's fine. We don't need to worry about that right now. We know what an entity is. We're going to have a game engine. Okay? We're going to have a abstract base scene class. We're going to have a gameplay scene. We're going to have a menu scene. We're going to have an entity manager. We're going to have entities. We're going to have assets. We're going to have animations. We have Vec2. We have actions. I'll get into the actions next time. And we're going to have a new way of loading components into entities and adding components that will be very, very interesting. And I'll get into that in the next lecture. The very last thing I want you to do in this lecture is to watch these two, like actually go and look at these right now. So for the people who are out there in the chat, let me copy this link. So I'm copying these links into the chat for people who are here. Immediately following this, because we're about to be finished this lecture, go watch these videos. They're very, very well done. And like this one, the importance of keyframes and run cycles. This is essentially describing why we're doing animations the way that we are and how effective that is. And this one, how old school graphics work, is going to make you really appreciate how nice we have it in this course for being able to just load and display as many sprites as we want. Someone said there was a slight typo here. Don't worry about it. This is not the code, right? I'm not going to go back and edit this image now, but thank you for mentioning the typo. So that's it. That is what I have for this lecture. And in the next lecture, we are going to be talking about something really cool. We're going to be giving the full breakdown of the assignment 3 architecture. We are going to be talking about actions. So no longer will we be working with raw keyboard input. We're going to be separating that into, we're going to be separating the pressing of keys from the doing of actions, which is really nice. And we're going to be talking about how we could implement replays in our game, which is really, really cool. So that's it. So keep working on assignment 2. And I will see you on Thursday for lecture number 10. See ya.